Now, today our topic is subgroup and its result. Already in the previous video, we are lecturing about the group. You all know that there are 4 conditions you have to satisfy. The same condition you have to satisfy for the subgroup. Now, subgroup means suppose G comma star be a group. Let G comma star be a group and H be a non-empty subset of G. And if H comma star, please be noted that if there is the operation is star, there should be the operation is star. If there is plus, there should be plus. If there is dot, there should be dot. If H comma star is a group, then we call then H comma star becomes the subgroup of G comma star, right? That means H is our non-empty subset of G, and if H comma star is a group, then H comma star becomes the subgroup of G comma star. Now, this is the formal definition of a subgroup. Now, if we have to check any result, any subgroup, then it is hectic or it is more time taking to show that all the 4 conditions of group, and again to show that this is a non-empty subset of G. Then which method we will apply? We will apply a result. What is that result? Let G comma star be a group and H be a non-empty subset of G. Then we have to show if AB belongs to H implies A star B also belongs to H, and A belongs to H implies S inverse belongs to H. If we can prove these 2 part or these 2 condition, then it will prove that H is subgroup of G. This result have a name that is called the 2-step theorem or 2-step condition. Now, also, this is called the 2-step test. Also, we can merge this condition into a single condition, which is called 1-step test. Here you have to show that if, obviously you have to first check that it is a non-empty subset of G, and next one you have to show that AB belongs to H implies A star B inverse belongs to H. The previous part is same, that is let G comma circle star be a group and H is a non-empty subset of G. Then if you can satisfy this condition, then H becomes subgroup of G. Clear? Now, this is the how we can check any non-empty set subgroup of any group. Now, we will take some example. We will take here an example. The subset H, X belongs to G such that X circle G equal to G circle X for all G belongs to capital G. This is your set. And H is subset of G comma circle. Prove that H comma circle is subgroup of G comma circle. Now, how we will proceed? Remember, one step test is very, very important to show this type of problem. So, first we have to check that this is non-empty. Now, just think about any one element which commute with every element of G. You know that. Please think of 5 seconds. 1, 2, 3, 4, 5. Time's up. Now, you know that the element identity. E circle G always gives you G and this is equal to G circle E. It commutes with every element. So, how we will proceed? Since E circle G equal to G circle E, then E belongs to H. That means X is here our E. So E belongs to H. So what we will prove that? Then H is a non-empty subset of G. So first condition we will satisfy. That is H is a non-empty subset of G. Next we will proceed. We will take two elements. A comma B belongs to H. If A comma B belongs to H, then it will commute with G. So we can write down A circle G equal to G circle A for all G belongs to capital G, and B circle G equal to G circle B for all G belongs to capital G. Now we have to show that A circle B inverse belongs to H, right? So how we will check this? Now first write down A circle B inverse circle G. Yeah. Now you know that it is commutative. So A circle B inverse circle G equal to can we write down this? AB belongs to H means AB already in G, as G set is the This is, if this is your H set, this is your G set, it is the larger set. AB belongs to here means AB already in G. G is group. If G is group, that means B inverse circle G, we can obviously write down G inverse circle B. That's whole inverse, right? I think there is no problem. Now, for all G, it is true. For all G. As G belongs to capital G, small g belongs to capital G, its inverse also belongs to the group. That's why we can obviously write down this line as this is true for all G. So this is also true for the G inverse. Now, we will change the right. So that will become a circle G circle B inverse. Again, we will write down here A circle G equal to G circle A. So as we take here the bracket, associativity, using the associativity, so we can write down this. So ultimately, we will get this result. And this means A circle B inverse belongs to your H. That means we are taking AB belongs to H. We will prove that A circle B inverse belongs to H. Using this one-step method, we will prove that H comma circle is a subgroup of G comma circle, right? Is it clear to everyone? So, we will solve another two problems. First one is, you have to determine H is a subset which contain 1, 2, minus 1, which is a subset of G set means your Z comma plus. You have to show that this H forms a subgroup under the addition of this G or not. Now, first, H is obviously non-empty subset of G. So, first condition is satisfied. Now, if you add 1 plus 2, that is equal to 3, but which is not belongs to H. That means H is not a subgroup of G equal to Z comma plus. Then if you understand this example, then solve for the next one. H equal to, this is the modulo class, 0 bar, 3 bar. G equal to Z6 comma plus. This is the plus 6 modulo. So, H is obviously a non-empty subset of G. This condition is satisfied. Now, taken two elements, 0 bar plus 3 bar, that is equal to 3 bar. 0 bar plus 0 bar, again it's a 0 bar. 3 bar plus 3 bar. As this is modulo 6, that means first you have to add, addition is 6, 6 divided by 6, remainder is 0. So, all these sums is belongs to your H. 0 bar inverse is 0 bar. 3 bars inverse is 3 bar. So all the elements inverse is also belongs to 0 bar belongs to H, implies 0 bar inverse that is equal to again 0 bar belongs to H. Same cases happen for the 3 bar. So all the two-step test, all the two-step test satisfied. So we call that H is subgroup of G comma plus or G comma plus 6. Clear? Just I will give you a homework. You will solve it, and if you're done with that, please comment me on the comment section that let G be an abelian group. Prove that the subset is equal to such P from G who will its own inverse forms a subgroup of G. Please try it, and if you are able to try, please answer me in the comment box. Today's video is up to that. If you are liking that videos, please like, share and comment.